Look at your hand. Look at the world around you. Everything appears smooth, continuous, a seamless tapestry of existence. We move through space without any bumps or jumps. It feels absolute. But what if this is all an illusion? What if, just like the screen you're watching this on, our universe is made of tiny, fundamental pixels? Pixels so small they are beyond our comprehension, yet they form the very foundation of everything we know. For decades, this was just a wild idea, a whisper on the edge of physics, but now we believe we have calculated its size. In this journey, we will travel to a scale where the laws of our world break down and the true, granular nature of reality is revealed. Prepare to question everything you thought you knew about space and time. To understand this cosmic pixel, we first need to understand a deep conflict, a war at the heart of physics. On one side, we have Einstein's general relativity. It is the theory of the very large. It describes gravity as a smooth, curving fabric of space-time. Think of it as a soft, rubber sheet where planets and stars create gentle dips and curves. It works perfectly for galaxies, stars, and planets. On the other side, we have quantum mechanics. This is the theory of the very small, the world of atoms and particles. Here, everything is chunky, discrete, and quantized. Energy doesn't flow smoothly, it comes in little packets, or quanta. For over a century, these two magnificent theories have been our best guides to the universe, but they refuse to work together. When you try to describe something both incredibly massive and incredibly small, like the center of a black hole, the equations break down into nonsense. They predict infinities, which is nature's way of telling us our theories are wrong. This clash is where our story begins. Physicists realized that to unite these two ideas, space-time itself could not be smooth. It too must have a smallest piece. So what is the size of this universal pixel? It is called the Planck length, and the number is almost impossibly small. It is approximately 1.6 times 10 to the negative 35 meters. That number is so minuscule it's hard to even visualize. Let's try. Imagine you took a single atom. Now imagine you magnified that atom to be as large as the entire known universe. The Planck length on that scale would be about the height of a single tree. It is the shortest possible distance that has any meaning in our universe. It is the fundamental limit, the final frontier of smallness. Any attempt to look at something smaller is not just technologically difficult, it is physically impossible according to our current understanding. It is the point where the very concept of distance and space simply ceases to exist. This incredible number wasn't discovered with a microscope. It was born from the mind of one of the fathers of quantum mechanics, Max Planck. At the turn of the 20th century, Planck was working on a completely different problem, trying to understand the light emitted by hot objects. He discovered that energy wasn't continuous but came in those discrete packets he called quanta. This was the birth of quantum theory. But he went further. He realized he could combine three of the most fundamental constants in nature, the speed of light, the gravitational constant, and his own quantum constant. By mixing these three cosmic ingredients, he could derive a fundamental unit of length, a unit of time, and a unit of mass. These weren't random numbers, they seemed to be baked into the universe's source code. He had found nature's own measuring stick. For decades, the Planck length was seen as a mere curiosity, a mathematical quirk. But as the conflict between relativity and quantum mechanics grew, physicists realized Planck might have accidentally stumbled upon the key to unlocking the universe's deepest secret. Now let's return to that clash of titans. General relativity's smooth world versus quantum mechanics' chunky world. Where does it matter most? At a place called a singularity. A singularity is a point of infinite density where a huge amount of mass is crushed into a zero-sized point. Our current theories predict two places where they exist, at the heart of every black hole and at the very beginning of the universe with the Big Bang. But infinity is a red flag in physics. It tells us our math is broken. The Planck length offers a brilliant solution. If space itself is made of these pixels, then you can never crush anything down to a zero-sized point. You can only crush it down to the size of one Planck length. There is a fundamental flaw to reality. This simple, elegant idea removes the dreaded infinities that have plagued physics for a century. The singularity vanishes, replaced by something incredibly dense and extreme, but finite. A black hole's center isn't an abyss of nothingness, it's a Planck-scale object. The Big Bang didn't start from an infinitely small point, it started from a pixel of space-time. So, what does space-time look like at this unimaginable scale? The picture physicists paint is one of breathtaking chaos. It's called quantum foam, or space-time foam. Imagine the calm surface of a deep ocean. From a distance, looks perfectly flat and smooth, but if you could zoom in to the microscopic level, you would see a turbulent world of tiny waves and bubbles constantly forming and vanishing. This is what many believe space-time is like at the Planck scale. Tiny virtual particles pop in and out of existence. Miniature wormholes and fleeting black holes might be bubbling away, creating a chaotic, energetic foam. Space and time as we know them become warped and twisted, losing their familiar meaning. It is a world of pure potential where the laws of cause and effect are blurred. Our smooth, predictable universe is just the large-scale average of this underlying wild reality. We sail on the calm surface, completely unaware of the raging quantum storm just beneath our feet. To truly grasp this, let's use a familiar analogy, a digital photograph. When you look at a high-resolution photo on your screen, it appears perfectly smooth and continuous. You see gentle gradients in color and soft curving lines. It looks like a perfect window into another reality, but if you zoom in closer and closer, you eventually hit a limit. The illusion of smoothness shatters. You see the individual pixels, tiny, uniform squares of color. The curve is revealed to be a staircase of tiny, straight lines. The gradient is just a collection of solid colored blocks. You have reached the fundamental resolution of the image. The Planck length suggests our universe works in exactly the same way. Our reality is so high resolution that we can live our entire lives without ever noticing the pixels, but they are there. Every motion we make, every planet that orbits a star, is ultimately a series of tiny jumps from one Planck-sized pixel to the next. Another powerful way to think about this is to imagine the universe as a magnificent piece of fabric, a cosmic tapestry. From a distance, you see the grand design, swirling galaxies, bright nebulae, intricate patterns. It seems like a single, continuous cloth. But if you were an ant crawling on its surface, you would discover that the fabric isn't a solid thing at all. It is woven from individual threads. The threads are the fundamental reality, and the grand pattern is the illusion that emerges from their interaction. These threads are the quanta of space. They weave together to create the reality we experience. You cannot have a piece of this fabric that is smaller than a single thread. It is the basic component. This is what theories like loop quantum gravity propose. They suggest that space-time is a network of interconnected loops or nodes. These connections, these weaves in the fabric, are what define space. Where there are no threads, there is no space. It isn't that the threads exist in space, the threads are space. This might sound like science fiction, but the Planck length is derived from very real physics. As Max Planck showed, you can find it by combining three numbers that govern our universe. First, there's g, the gravitational constant. This number sets the strength of gravity, the force that shapes the universe on the largest scales. Second, there's c, the speed of light in a vacuum. This is the ultimate speed limit of the cosmos, connecting space and time. And third, there's h bar, or h bar, the reduced Planck constant. This is the heart of quantum mechanics. It defines the chunkiness of the quantum world. Each of these constants rules a different domain of physics. But when you mix them together in just the right way, all the units like meters and kilograms cancel out, leaving you with a pure, fundamental unit of length. It's as if the universe is whispering its own secret recipe to us. It's telling us that the nature of gravity, the speed of light, and the quantum world are all deeply, profoundly interconnected at this fundamental scale. But is this just a beautiful theory, a piece of mathematical poetry? Or is there a way to actually prove that space-time is pixelated? This is one of the greatest challenges in modern physics. Detecting the Planck length directly is far beyond our current technology. However, scientists are incredibly clever. They are looking for indirect evidence. One idea is that this graininess of space-time might affect how light travels over vast cosmic distances. Imagine light as a wave traveling through a medium. If the medium is perfectly smooth, waves of all colors or energies will travel at the exact same speed. But if the medium is grainy, like water is made of molecules, then very high-energy, short-wavelength light might interact with the grains differently than low-energy light. It might be slowed down by an incredibly tiny amount. Over billions of light-years, this tiny delay could add up. By observing powerful gamma-ray bursts from the distant universe, we could look for this effect. If high-energy photons arrive slightly later than low-energy ones from the same explosion, it could be the first tantalizing hint that we've seen the pixels of reality. This leads us to an even more bizarre and profound idea known as the holographic principle. It suggests that the information content of any volume of space is not determined by its volume, but by its surface area. Think about a credit card hologram. A two-dimensional surface contains all the information needed to project a three-dimensional image. The holographic principle proposes that our universe might be like that. The 3D reality we experience could be a projection of information stored on a 2D surface at the edge of the cosmos. And how much information can be stored? There is a limit. The smallest possible unit of surface area that can hold 1 bit of information is a square with sides of 1 Planck length, and this is called a Planck area. It's as if the universe is a giant hard drive, and its storage capacity is written on its surface in pixels the size of the Planck area. This isn't just a wild analogy, it's a concept that emerged from studying the physics of black holes, and it's taken very seriously. It suggests that information, not matter or energy, might be the most fundamental thing in the universe. What does this mean for the greatest mysteries in the cosmos, like black holes? According to general relativity, the center of a black hole is a singularity. But as we've discussed, the Planck length forbids this. So what happens instead? When a star collapses, its matter gets squeezed denser and denser, but it can't be squeezed smaller than the Planck scale. Instead of a singularity, you might get a Planck star or some other exotic object made of matter at its absolute maximum density. Furthermore, the event horizon, the point of no return of a black hole, also has fascinating properties at the quantum level. According to the holographic principle, all the information about everything that ever fell into the black hole is not lost in a singularity, but is encoded on the surface of the event horizon, with each bit of information occupying 1 Planck area. So, a black hole is like a cosmic vault with a record of its history written in quantum pixels on its surface. Let's rewind the cosmic clock, all the way back to the beginning. The Big Bang. Our standard model says the universe began from an infinitely hot, infinitely dense singularity. Again, that troublesome infinity. But with Planck physics, the story changes. The universe didn't begin from a point, it began as a point, a single Planck-sized pixel containing all the energy of the future cosmos. This primordial atom was the minimum possible size for our universe. We cannot ask what came before it because the concepts of before and space didn't exist yet. Time and space were born with this Planck-scale object. The Big Bang, then, was not an explosion in space, but an explosion of space itself, as this single, hyperdense pixel began to rapidly expand, creating more pixels of space as it grew. It's a much neater, more finite picture of our origins. It places a concrete physical boundary on our past, giving us a true moment zero that is described by physics, not by an infinity. One of the leading theories that builds upon this idea of a granular universe is called loop quantum gravity, or LQG. It takes the idea of a pixelated universe literally. In LQG, space-time is not a smooth background. Instead, it is a dynamic, evolving network. Imagine a mesh made of tiny, indivisible loops. These loops are the quanta of the gravitational field. They are the fundamental atoms of space itself. Where these loops intersect, they create nodes. Each node represents a tiny, indivisible chunk of volume, a Planck scale volume. The connections between these nodes, the loops, define the geometry of space. This network isn't static, it's constantly changing and evolving, like a shimmering quantum spiderweb. The smooth, continuous space we perceive is just a low-energy approximation of this incredibly complex underlying network. In this theory, there is no space between the loops. The loops are space. Loop quantum gravity isn't the only game in town. The other major contender for a theory of everything is string theory, and it has its own equally fascinating take on the smallest scales. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny, one-dimensional vibrating strings. Different vibrations of these strings give rise to all the different particles we see: electrons, photons, quarks, and so on. It's a beautiful idea, like a cosmic symphony, where each note is a different particle. So where does the Planck length fit in? In string theory, the strings themselves are thought to be around the Planck length in size. This is their fundamental scale. You cannot probe inside a string. They are the bottom floor of reality in this model. So, while the language is different, a network of loops versus tiny vibrating strings, both of these leading theories arrive at the same conclusion. Reality is not infinitely divisible. There is a fundamental Planck-scale entity that builds the universe from the ground up. This granular structure of space-time raises a fascinating question. Does this mean space is not truly empty? Our classical picture of a vacuum is one of perfect nothingness, but quantum mechanics changed that. It introduced the idea of the quantum vacuum, a sea of virtual particles constantly popping in and out of existence. Now, with the concept of quantum foam, we go even further. The vacuum of space, at its most fundamental level, is a raging, chaotic landscape. It is not empty, it is filled with the potential for all of reality. The energy inherent in this space-time foam, sometimes called vacuum energy, is theoretically enormous. This has been a huge puzzle in physics because if this energy had the gravitational effect we expect, the universe would have blown itself apart. Resolving this discrepancy is a major goal of quantum gravity research. But the core idea remains: the nothingness between the stars is, at the Planck scale, the most complex and energetic something imaginable. If space is pixelated, what about time? Max Planck's calculations didn't just give us a fundamental length, they also gave us a fundamental unit of time. It's called the Planck time. It is the time it would take for a photon traveling at the speed of light to cross a distance of 1 Planck length. Its value is about 5.39 times 10 to the negative 44 seconds. This is the shortest possible unit of time that has any physical meaning. It is the tick of the universal clock. Just as you cannot have a distance shorter than the Planck length, you cannot have a duration of time shorter than the Planck time. It is the quantum of time. This suggests that time, like space, does not flow smoothly like a river. Instead, it progresses in a series of incredibly rapid, discrete steps. Our universe is like a movie, but with a frame rate so impossibly fast, we can never perceive the individual frames. Each frame is 1 Planck time long. The idea of pixelated time is perhaps even more mind-bending than pixelated space. What does it truly mean? It means that the concept of now is not an infinitely thin slice between past and future. The present moment has a minimum duration. It also means that change in the universe is not continuous. An object doesn't move smoothly from point A to point B. Instead, the entire configuration of the universe updates itself, one Planck time at a time. It is a series of cosmic snapshots. In one snapshot, a particle is here. In the next snapshot, it is there. There is no in-between. This resolves some famous paradoxes like Zeno's paradox of the arrow, which argued that for an arrow to reach its target, it must first travel half the distance, then half of the remaining distance, and so on forever, meaning it can never arrive. In a pixelated universe, the arrow simply makes a finite number of jumps and arrives at its target. The infinite division is not allowed by nature. The speed of light, AC, is a cornerstone of this entire concept. It's the cosmic speed limit, the rate at which information can travel through spacetime. The relationship between the Planck length and the Planck time is defined by this speed limit. They are inextricably linked. This link suggests that the granular nature of space and time might have observable consequences for the speed of light itself. As mentioned before, some theories predict that very high-energy photons might travel at a slightly different speed through the quantum foam than low-energy photons. This is called a violation of Lorentz invariance, which is the principle that the laws of physics are the same for all observers, regardless of their speed. Finding such a violation would be a monumental discovery, a Nobel Prize-winning achievement. It would be the first direct experimental proof that Einstein's smooth picture of spacetime breaks down and that a deeper quantum structure lies beneath. Observatories around the world are watching the skies, hoping to catch a glimpse of this tiny, telltale effect from the most violent events in the universe. At this point, it's important to address a common myth. When people hear about a pixelated universe, they often jump to one conclusion. This means we are living in a computer simulation. It's an exciting and popular idea, fueled by science fiction and philosophy. However, just because the universe appears to be digital at its core does not automatically mean it is an artificial simulation. It could simply be the inherent nature of reality itself. A photograph is pixelated, but it represents a real analog world. The universe having a fundamental resolution might just be a basic law of physics in the same way that energy coming in quanta is a basic law. It doesn't require a computer or a programmer. The universe could be a self-contained, naturally digital system. While the simulation hypothesis is a fun thought experiment, it is not a scientific conclusion we can draw from the existence of the Planck scale. The reality is, perhaps even more profound, the universe wrote its own code. So, how are scientists trying to test these ideas? One of the most direct attempts was an experiment at Fermilab called the holometer. Its purpose was to test the holographic principle by looking for a fundamental jitter in spacetime itself. The idea was that if our 3D space is a projection from a 2D surface, there might be a fundamental limit to the information content of spacetime, which would manifest as a tiny, random noise or uncertainty in the position of things. The holometer was an incredibly sensitive L-shaped laser interferometer designed to detect motion at a scale far smaller than a proton. It was looking for a specific type of holographic noise that would cause spacetime to jitter in a correlated way. After years of collecting data, the experiment did not find this specific type of noise. While this result ruled out some simpler holographic models, it doesn't kill the idea entirely. It just tells us that if spacetime is a hologram, its nature is more subtle and complex than our initial theories suggested. The search continues. Beyond ground-based experiments, we are using the entire universe as our laboratory. As we discussed, gamma-ray bursts, or GRBS, are one of our best tools. These are the most powerful explosions in the universe since the Big Bang, caused by collapsing massive stars or merging neutron stars. They release a torrent of radiation across the entire spectrum, including very high-energy gamma rays, and, crucially, they happen at immense distances, billions of light-years away. This makes them perfect probes for quantum foam. Even a minuscule change in the speed of light, depending on its energy, would be amplified by this vast travel time. The Fermi Gamma Ray Space Telescope has been staring at these bursts for over a decade, precisely measuring the arrival times of photons of different energies. So far, the results have been inconclusive. No definitive delay has been found, which puts tight constraints on some theories of quantum gravity. But every new burst is a new opportunity to find the first crack in Einstein's smooth spacetime. The quest to understand the Planck scale is the quest for a theory of quantum gravity. It is the holy grail of modern physics. Theories like loop quantum gravity and string theory are our current best attempts, but the road ahead is long. Future experiments and observations will push our understanding further. Gravitational wave observatories like LIGO and the future LISA might be able to detect signatures of quantum gravity from the mergers of black holes, or even from the echoes of the Big Bang itself. New, more powerful particle accelerators could, in theory, reach energies where quantum gravitational effects become apparent, though this is a distant prospect. The most likely path forward is a combination of theoretical breakthroughs and clever astronomical observations. Physicists will continue to refine their models, looking for unique, testable predictions. And astronomers will continue to scan the cosmos, using the most extreme events in the universe as a natural laboratory to test those predictions. It is a slow, painstaking process, but it is a journey towards the deepest possible understanding of our reality. The implications of a pixelated universe stretch beyond physics and into the realm of philosophy. For millennia, thinkers have debated whether reality is fundamentally continuous or discrete. Is it infinitely divisible, or is there a bottom level? The Planck scale suggests that the discretists were right. This has profound consequences for our ideas about infinity. If space, time, and energy are all quantized, it may be that true infinities do not exist in the physical world. They may only be concepts in mathematics. This would mean the universe, while incomprehensibly vast, could be fundamentally finite. Finite in its resolution, finite in its information content, and perhaps even finite in its ultimate extent and duration. This doesn't make the universe any less majestic. In fact, it can make it feel more knowable, more tangible. It transforms it from an abstract, infinite void into a concrete, physical system governed by rules that we have the potential to fully understand. It's a universe we can get our minds around, even if its scale still boggles the imagination. Let's revisit this idea of the graininess of space-time. It's a crucial concept to internalize. We are used to thinking of space as a smooth stage on which the drama of the universe unfolds. But quantum gravity tells us the stage itself is an actor. It is a physical object with a structure. This graininess is not like the grain in a piece of wood, which is a pattern within the wood. The grains are the wood. Similarly, the Planck scale grains don't exist in space-time. They are space-time. This means that at the most fundamental level, the universe might be more like a network or a computational process than a physical place. Concepts we take for granted, like a precise location, might not be fundamental. A particle's location might only be defined by its relationship to the other nodes in the space-time network. It's a radical shift in perspective, moving from a background-dependent view of physics to a background-independent one, where the universe creates its own stage as it goes along. Another beautiful analogy for this is a pointillist painting, like those by Georges Seurat. When you stand back from the painting, you see a rich, detailed scene: people in a park, a boat on a river. The colors blend seamlessly, the lines are soft and natural. It looks like a continuous image, but as you walk closer, you realize the entire painting is composed of thousands of tiny, individual dots of pure color. There are no blended brushstrokes, no continuous lines. The entire complex scene is an emergent property of the simple, discrete dots and their placement. Our universe might be nature's grandest pointillist masterpiece. The Planck-scale dots of space-time, when viewed from our macroscopic perspective, create the emergent illusion of a smooth, continuous reality. The laws of physics as we know them, like gravity and electromagnetism, are the large-scale patterns that emerge from the simple, underlying rules governing these fundamental dots. How does this radical idea change our most basic concept of motion? In our classical world, motion is smooth and continuous. To get from one place to another, an object must occupy every single point in between. But if space is pixelated, this is no longer true. Motion becomes something more akin to a movie projector. The universe displays one frame, then the next, at a rate of one frame per Planck time. In one frame, an electron is at pixel A. In the next frame, it is at pixel B. It was never between A and B. It simply ceased to exist at A and began to exist at B in the next instant. This might sound strange, but it's very much in the spirit of quantum mechanics, where particles can perform quantum leaps between energy levels in an atom without ever existing in the states in between. Motion, at its most fundamental level, might not be about traveling through space, but about the pattern of existence rippling across the underlying grid of space-time. With a minimum length, time, and mass, we can also derive a maximum possible energy and temperature. This is known as the Planck temperature. It is an almost ludicrously high number, 1.41 times 10 to the 32 Kelvin. This is the absolute hottest that anything can possibly get. At this temperature, the energy of individual particles becomes so immense that their gravitational pull would be strong enough to create their own tiny, transient black holes. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, are all thought to merge into a single, unified superforce at this energy scale. This is the temperature the universe is believed to have been at in the very first instant of its existence during the first unit of Planck time after the Big Bang. It is the ultimate energy frontier, a state of matter, an energy so extreme that our current physics cannot fully describe it. It is the true firewall at the beginning of time. It is crucial to acknowledge the limits of our knowledge. Everything we've discussed about the Planck scale is at the very edge of theoretical physics. It is the boundary where our most trusted theories fail, and we must rely on new, unproven ideas. While the Planck length is derived from well-known constants, its physical interpretation as a pixel of space is still a hypothesis. Theories like loop quantum gravity and string theory are mathematically sophisticated and beautiful, but they currently lack direct experimental evidence. We are like 15th century map makers trying to draw a map of the entire world based on reports from a few sailors who have only glimpsed a new coastline. Our map of the Planck scale is incomplete and likely contains many errors, but it is our best attempt to chart this unknown territory. The process of science is to make these bold hypotheses and then test them relentlessly. What we've shared is the current cutting-edge story, but it's a story that is still being written. Let's recap the incredible journey we've been on. We started with the familiar, comfortable illusion of a smooth, continuous world. We discovered a deep conflict at the heart of physics, a clash between the smooth world of Einstein's gravity and the chunky world of quantum mechanics. This conflict led us to the idea of a fundamental limit, a smallest possible unit of space, the Planck length. We visualized this scale, so small it defies imagination. We explored the chaotic quantum foam that may define spacetime's true nature. We used analogies of digital screens and woven tapestries to grasp this new reality. We saw how this simple idea could solve the problem of infinities in black holes and the Big Bang. We have journeyed from a simple observation of our surroundings to the very foundations of the cosmos, to the first tick of the universal clock, and to the ultimate resolution of reality itself. So, the next time you pour a glass of water and watch its smooth, flowing surface, remember the illusion. You are witnessing the collective behavior of trillions upon trillions of quantum events, a dance of emergent properties playing out on a stage made of indivisible pixels. The universe is not the simple, analog place it appears to be. It is a profoundly digital entity with a resolution so fine that it creates a near-perfect imitation of smoothness. This discovery does not diminish the beauty of the world, it enhances it. It adds a hidden layer of complexity and wonder, a secret structure just beneath the surface of everything. It connects the largest galaxy to the smallest possible vibration of a string, all through a shared fundamental and granular reality. Our universe is both a grand painting and a collection of tiny dots, a flowing river and a series of discrete steps, a grand cosmic story written in the smallest possible alphabet. We have traveled to the very bottom of reality, to a place where space and time dissolve into a foam of pure potential. The idea that our universe has a pixel size is one of the most profound in all of science. It changes everything. It tells us that the cosmos, for all its vastness, may be finite in its detail. It gives us a framework to unite our greatest theories and to ask even deeper questions about our origins and the nature of information itself. The world around you will still look smooth, but now you know its secret. Beneath the seamless veneer lies a hidden, vibrant, and granular reality. Thank you for joining us on this mind-bending journey to the edge of space and time. So, what does this discovery make you feel? Awe, insignificance, or a deeper connection to the intricate workings of the cosmos? Share your thoughts in the comments below.